So today we're going to be talking about series, so total response of series RLC circuits. And it's going to be very similar to what we did with the total response of parallel RLC circuits, except that we're going to have a slightly different second order differential equation. Okay? So let's say that we have the following circuit. I have some current source IS. Let me think about how I want to draw this. Here's R, here's L, here's C. This is some resistor that literally doesn't matter at all. All right, so that should successfully disconnect my current source while leaving my RLC as a thing. Okay, so we have a system like this where we should expect to see that some current flows through, some portion of IS flows through our resistor, which is in series with our inductor, which is in series with our capacitor. At DC steady state, because our inductor current is non-zero, our inductor will have some amount of stored energy. And then as our switch changes state, we enter into our transient condition, and we should see that the inductor gives energy to the capacitor, and some portion also gets absorbed by the resistor. And then over time, all of the stored energy in the system gets converted into heat by the resistor. So a very, very similar situation to what we had previously, except that now all of our elements are connected in series as opposed to being connected in parallel. So I'm going to define my common current to be I of T. And then this will be the voltage drop VL of T. This will be the voltage drop VC of T. And this will be the voltage drop VR of T. And I've chosen these particular polarities such that the current is flowing into the positive polarity terminal of all of them. So applying Kirchhoff's voltage law around this loop, we wind up seeing that VR plus VL plus VC is equal to 0 during the transient condition. I can express all three of those voltages in terms of my common current I. So using Ohm's law, we're going to have R times I of T. The voltage drop across an inductor is L times the derivative of the current. And then the voltage drop across the capacitor is going to be 1 over C times the integral of the current. Plus some initial condition on the capacitor voltage. And I have an integral differential equation, which I fundamentally don't care for. So once again, I will take the derivative of both sides, giving me a second order differential equation. So I'm going to put my second derivative term first. So that's going to look like L times the second derivative of my current plus R times the first derivative of my current plus 1 over C times my current. And now I'm going to divide both sides through by L so that my second derivative term has a coefficient of 1. So that's going to leave me with the second derivative of current with respect to time plus R over L times the first derivative of current with respect to time plus 1 over LC times my current is equal to 0. And I have a nice, neat, homogeneous second order differential equation. We will guess that I of t must be of the form AE to the ST, much like we did with our parallel RLC circuit. And we're going to substitute in this guess into our differential equation. So the second derivative of this guy is going to look like S squared AE to the ST. Then we're going to have R over L times S AE to the ST plus 1 over LC times AE to the ST is equal to 0. And now I'm going to factor things out. So there's a common factor of A. Here's S squared plus R over L times S plus 1 over LC e to the ST is equal to 0. And I now have my characteristic polynomial. Which is a second order polynomial. So I can use the quadratic equation, right? So this thing will be equal to 0 when S1 comma 2 is equal to negative R over L plus the square root of R over L squared. So let's see, minus 4 times 1 over LC, all divided by 2. Moving that 2 from the denominator up to the is going to look like negative R over 2L plus or minus the square root of R over 2L quantity squared minus the square root of 1 over LC quantity squared. And we now have it in exactly the same form as we had for our parallel RLC circuits. And we can see very easily that alpha for a series RLC circuit is equal to R over twice L, and omega naught is equal to the square root of 1 over LC. And we're now at a point where our analysis for this type of circuit is literally identical to a parallel RLC circuit, so I don't need to derive anything else. Okay. So this is already all spelled out for you in your table and all of that kind of good stuff. For a series RLC circuit, alpha is equal to R over 2L. For a parallel RLC circuit, alpha was equal to 1 over twice RC. Omega naught is equal to the square root of 1 over LC in both cases. And all of our response equations will literally be the exact same thing. So we finished up with the lecture portion of this in a tight 12 minutes. Isaiah? So I could make this look like a form where it's going to be negative alpha plus the square root of alpha squared minus omega naught squared. So that both things are squared inside of the square root. Literally just arbitrarily making it. Omega naught as a quantity has a special meaning, and so that's why I wanted something in that form. And then to make the math work out, I needed to take the square root and then square it. Yeah. All right, so I believe before the break, we worked an example problem with a parallel RLC circuit that was overdamped. So today I would like to work a series RLC circuit where it is critically damped because I want to show you some potential issues you might have with the LT spice. And if we have time, I'll also work an underdamped problem. And if I don't have time to do the underdamped problem today, that'll be the first thing that we do on Friday's class meeting, which is literally just designated for working more example problems for this material. So think of it as effectively extended office hours where you can ask any questions you might have about your homeworks and all that kind of jazz. That's what I have planned for this Friday. All right, so because I need to make sure that this circuit is critically damped, I need to just figure out some parameters here. So somebody hit me with a value for a resistor. 2 ohms, okay. Give me a value for an inductance. 1.6 Henrys, all right. So for the circuit to be critically damped, we need alpha to equal to omega naught. So effectively, I'm just going to manipulate things to solve for C and then plug in those values so that we'll know what C we need. So R over 2L is equal to square root of 1 over LC. So that means R squared over 4L squared is equal to 1 over LC. So LC would be equal to 4L squared over R. So C would be equal to, sorry, that should be R squared. Divide both, so 4L over R squared if my algebra worked out. Anybody see any issue with that? Okay. So plugging in the numbers that you guys gave me, 4 times 1.6 over 4. Oh, well, that's going to be easy. That's just 1.6 farads. Yep. All right. So just to quadruple check things here, let's draw a circuit. This guy does not matter. That's intentional. So for this one, I'm working it as a total response problem. So we had no energy stored at t is equal to 0 minus, and then we'll see that it's going to charge as time goes on. That being said, that will make a difference here. So let's make this a 1 ohm and that one a 1 ohm, so that the equivalent resistance is going to look like 2 ohms, which is what we settled on earlier. And which quantities do we want to solve for? VL of t? Okay. So let's solve for the inductor voltage. Just to make sure things are okay here, alpha is going to be REQ over 2L. So during the transient condition, looking at a dead network, we would take our two energy storage elements out. So these guys are going to be an open circuit, and we're going to look in this way. We would see the 1 ohm resistor shorted and connected to this 1 ohm resistor with this 5 amp source as an open circuit. So we would see 1 ohms in series with 1 ohms is 2 ohms. So I just want to be clear about that. So this is going to be 2 ohms divided by 2 times 1.6 Henry, which is 0.625 nepers per second. Omega naught is the square root of 1 over LC, which is the square root of 1.6 Henries, 1.6 farad. Comes out to be 0.625 radians per second. I just wanted to make sure I didn't screw up the algebra earlier. So very obviously this will be a critically damped circuit because alpha is equal to omega naught. Okay, just wanted to double check that. So now let's do our analysis at t is equal to 0 minus. So at t is equal to 0 minus, our switch is closed on the short circuit thing. So we have this 1 ohm resistor, 5 amps, short circuit, 1 ohm. Our inductor looks like a short circuit. Our capacitor looks like an open circuit. Here's I of 0 minus, VC of 0 minus, VL of 0 minus, and we can see by inspection that I at 0 minus is 0 amps, VL at 0 minus is 0 volts, and VC at 0 minus must also be 0 volts. By doing Kirchhoff's voltage law around this right-hand loop, if there's no voltage drop across the 1 ohm resistor, because there's no current flowing through it, then there can't be a voltage drop across the capacitor either. So are we all okay with our analysis at t is equal to 0 minus, where when our RLC circuit isn't connected to a source, we don't have any energy stored? All right. At t is equal to 0 plus, this is what our circuit's going to look like. So here we have a 1 ohm resistor. Here's our 5 amp source. Because the current flowing through our inductor was 0 amps, now our inductor is going to look like an open circuit, so a 0 amp current source. Because the voltage drop across our capacitor was 0 volts, it's now going to look like a 0 volt source or a short circuit. So here's I at 0 plus, VC at 0 plus, and VL at 0 plus. I at 0 plus must equal I at 0 minus, which was 0 amps. VC at 0 plus must equal VC at 0 minus, which was 0 volts. VL may have changed. So my question to you guys is, did it? Oh, thank you. For that, Walker, this should still be a 1 ohm resistor. Doesn't change the answer to the question though. What's VL at 0 plus? 0. So is it 0 volts or is it 5 volts? Because I'm hearing both. I disagree. So no current is flowing through this 1 ohm resistor, which means the positive polarity terminal of our inductor could be here. The negative polarity terminal would be here. So the voltage drop across this inductor is going to be the same as the voltage drop across this 1 ohm resistor on the left. All 5 amps flow through the 1 ohm resistor because it's the only path. Therefore, VL at 0 plus looks like 5 volts to me. Anybody have a problem with that analysis? Okay. Now we analyze at t is equal to infinity. So at t is equal to infinity, our switch is still closed where it currently is. So this 1 ohm resistor in parallel with this 5 amp source. Here's our 1 ohm resistor. Because we're at DC steady state again, our inductor is going to look like a short. Our capacitor is going to look like an open circuit. Here's IL at infinity, VC at infinity, VL at infinity. By inspection, IL at infinity is 0 amps. VL at infinity is 0 volts because it's the voltage drop over a short circuit. VC at infinity will be equal to what? 5 volts. Right. For the exact same reasons that VL at 0 plus was 5 volts. Go away. Oh, it did go away. The positive polarity terminal of this voltage could be slid all the way over here without any issues because there's no voltage drop anywhere along here. The negative polarity terminal is over here, so VC is the same thing as the voltage drop across the 1 ohm resistor on the left, which is just 5 volts. All right, so we did all of our analysis at 0 minus, 0 plus, and infinity. We have already established what alpha and omega naught are. We know that they're equal to each other so that this is a critically damped circuit. We're trying to solve for the inductor voltage. So I'm going to say that my quantity Y of t from my table is going to be the inductor current, and my derivative-based relationship will then be for the inductor voltage, okay? So because this is a critically damped circuit, I can say that I of t is of the form, oh gosh, let's see, A1 t e to the negative alpha t plus E2 e to the negative alpha t plus I at infinity. Right, I don't have the table in front of me, so if I made a mistake, please tell me, but I believe I remember it correctly. Okay. I at 0 plus is then just going to be A2 plus I at infinity. Because t at 0 is going to make this whole term go away. Right? So we should be able to directly solve for the quantity A2 here, right? So I at 0 plus was 0, I at infinity was also 0, so it seems like A2 is 0. VL is L di by dt. So that's going to be Oh, somebody tell me so I don't have to do this calculus in my head, please. Yep. All right. Thank you for that. So VL at 0 plus, actually, sorry, this whole thing should be multiplied by L. Sorry, I missed that, but thank you. So that's going to be L times, that first term is going to go away. So we're going to have A1 minus alpha A2. Since A2 is 0, that term is also going to go away. And so we can see very easily that A1 should just be VL at 0 plus divided by L. So that's 5 volts divided by 1.6 Henry is 3.125. What should the units here be? I very much disagree that it's volts. Also not amps. So let's look, we can figure it out actually looking at the dimensions of stuff and all that kind of stuff in a moment, but A1 is a coefficient that's being multiplied by time and is giving us a current. So I would argue that this needs to be amps per second in order for the math to work out. If we look at this, 5 volts divided by 1.6 Henry, a Henry is a volt second per ampere. So the volts are going to cancel each other out. We're going to have 1 over amps. So it's going to move amps up to the numerator, and then our seconds is still going to be here. So it's going to be amps per second. So 3.125 amps per second. So VL of T is going to be, let's see, negative alpha L times A1 T e to the negative alpha T plus L times A1, because A2 is 0, I'm just leaving that part out, e to the negative alpha T. And so I'm just going to substitute stuff in. So negative 0.625 times 1.6 times 3.125 comes out to be negative 3.125 t e to the negative 0.625 t. 1.6 times 3.125 plus 5 e to the minus 0.625 t. So let's get LT Spice popping and make sure that we didn't make any mistakes. All right. What? No. Okay. All right, so let's see. We have a 1 ohm resistor over here. I'll put units on it in a moment. That's the wrong thing. at the way the volt has a positive terminal on the top, maybe on the bottom? I think so. You were saying about the inductors or just things in general? Yeah, I think in general, before you rotate it, positive polarity is on top. And then, or sorry, yeah, because it comes out vertically originally, right? Yeah, so I think positive polarity is on top, and then it rotates it by 90 degrees, which I think would make positive polarity on the right, and then rotating again, positive polarity on bottom, and then another time, positive polarity on the left. I don't usually pay attention to that. I just look at what direction the current probe is telling me, and then if I need to include a negative sign to make it work right, I do, because I'm lazy. All right. So that's all that. 1 ohm, 1 ohm, 1.6, 1.6. As I mentioned previously, I always choose to put my ground terminal at the negative polarity terminal of my capacitor voltage, which would be down here at this bottom node. I'm going to label the positive polarity terminal with VC up here. I'm going to have to put some initial conditions in. So dot IC, the voltage at node VC is equal to 0. Dot IC, the current flowing through inductor L1 was 0. Because alpha was 5/8 of a second, let's run this for like 3 seconds. Oh, I forgot to tell this that it was a 5 amp current source. My bad. That. All right, so I need the voltage drop across my inductor, positive polarity on the left. So I'm just going to mouse over here. This node is V at node 2. So add trace, the voltage at node 2 minus the voltage at node VC is the voltage drop across my inductor. Oops, that did not come out exactly how I wanted it. Minus V at VC. There we go. And let's change the color of that to blue. Going to add a trace. So let's see, negative 3.125 times time times exp of negative 0.625 times time plus 5 times exp negative 0.625 times time. And change that to red just so it's easier for you guys to see. All right, so looks like the red curve completely overlaps the blue curve. Just to double check things here, our scale on the left-hand side of the screen ranges from positive 5.4 down to negative 1.2. Our scale on the right-hand side of the screen ranges from positive 5.4 down to negative 1.2. So it looks like we did everything correctly here. What I really wanted to point out to you guys is that we literally cannot use units in our mathematical expression for this guy because it does not know how to interpret this being amps per second. It's like it doesn't like a fraction in the units. So you're not, yeah. For an overdamped circuit, you could always say that this coefficient had a unit of amps or volts where appropriate, and it actually won't even bother with the scaling factor on the right-hand side of the screen. But for a critically damped circuit, you have to explicitly check the scaling factors. Yes?
So it says D and 002. Where is that on the screen?
Right here. So voltage at this node is V, or effectively it's saying this node is VN002. So this is the positive polarity terminal minus VC, which was the negative polarity terminal of my inductor. So we're having to explicitly give it 2 points because, go away. Okay. We're having to give it 2 points because our inductor isn't measured, like one of the terminals isn't at ground. So if we just did this node right here, it would actually be the voltage drop across the inductor plus the voltage drop across the capacitor, which isn't what we're exactly looking for. So that's a circuit's one thing, right? The voltage is defined as the difference in electric potential between 2 points in a circuit. Since we want the voltage drop across the inductor, I'm choosing the different 2 points in the circuit with respect to ground and taking the difference of them. All right, any questions about this particular guy? Isaiah, what's up? Sure. Absolutely. So let me do this formally because I just glossed over it pretty quickly. All right, so during the transient condition, our circuit is going to look like this. So here's our 1 ohm resistor. Here's our 5 amp source. Here's a 1 ohm resistor. Here's our inductor. Here's our capacitor, right? So this is what it looks like during the transient condition, where we don't know really what the inductor and what the capacitor are doing. We're finding the equivalent resistance with respect to our energy storage elements. So we're going to take both of them out kind of as a unit, okay? So if I take both of these out at the same time, I'm going to leave behind an open circuited set of terminals located here and here. Because I'm finding the equivalent resistance, I need to look at a dead network, which means I turn off my current source. And I'm looking in where my energy storage elements were. So that's why I see 1 in series with 1. So that is the process always, always, always for finding the equivalent resistance in these circuits. We take the energy storage elements out. So they need to either directly be connected in series or directly connected in parallel. Look in through the terminals that are left behind with a dead network.
Separately. Like if they're in parallel, what if they're not directly in parallel?
So if we don't have a series RLC circuit or we don't have a parallel RLC circuit, we can't find the equivalent resistance in this way. So next Monday, we are going to cover the total response of general RLC circuits, meaning circuits that aren't specifically series RLC circuits or parallel RLC circuits. And we will find out that there isn't a short and easy way to find REQ effectively. So we're not going to have a single generic equation for alpha or actually omega naught. It's going to depend on all of the elements in the circuit. And so what we're going to spend the overwhelming majority of our time doing is actually writing the second order differential equation and then using that to figure out what alpha and omega naught are. So you accidentally led us into what we're covering next week. Yes.
What would you change the initial condition?
I don't fully understand the question.
The dot IC of UVC, that's initial.
Right, so that's the initial condition on the capacitor voltage and the initial condition on the inductor current. So way back here, When we analyze the circuit at t is equal to 0 minus, I'm putting in this result and this result as our initial conditions. Because our simulation is for everything greater than 0 plus after our switch change states. So we have to explicitly specify what the inductor was doing and what the capacitor was doing before the switch was in change states so that it knows how to process the originally stored energy if there was any. Yep. Time for a underdamped circuit. Sorry. All right. All right, so for an underdamped circuit, we need omega naught to be greater than alpha. Do we want this to be a series RLC circuit or a parallel RLC circuit? Because at this point, it doesn't matter. Parallel, okay. So for a parallel RLC circuit, we know that alpha is supposed to be 1 over twice RC. And we know that omega naught is square root of 1 over LC. For underdamped, we know that omega naught needs to be greater than alpha. So that means that the square root of 1 over LC has to be greater than 1 over twice RC, or 1 over LC has to be greater than 1 over 4 R squared C squared. Which means LC needs to be less than 4 R squared C squared. All right, so somebody give me, I just need numbers for either a resistor, capacitor, inductor. I need 2 of the 3. So R is equal to 5 ohms, C is equal to 1 farad. So L will need to be less than 4 R squared times C, or 4 times 5 ohms squared times 1 farad. So 4, it's just 100, right? So 4 times 25 times 1. So L just needs to be less than 100 henries. So L is 1 Henry. Okay. That should work out okay. We'll check stuff here in a moment. So let's come up with a circuit. So this is a parallel RLC circuit. Let me move this over. All right, what do we want to solve for? I see. Okay. All righty. So let's double check things and just make sure that this is actually a underdamped circuit before we do all of our another analysis and all that kind of stuff. Toby.
Just the inductor and capacitors that have to be in parallel with each other or series?
Nope, the resistance has to be in either, so if it's a series RLC circuit, the resistance has to be in series as well. If it's a parallel RLC circuit, the resistance has to be in parallel as well.
Like equivalent resistance.
Right, the Thevenin equivalent resistance when looking at a dead network. So for instance, right here, with this switch closed, this 10 is going to be in parallel with this 10, which is going to look like 5. And so we'll have 5 in parallel with 1 in parallel with 1, and that 2 amp source is going to be an open circuit. If I had put a voltage source here, though, we would have a problem because I would have no resistance in parallel with an inductance in parallel with a capacitance, which is actually going to look like an LC resonator tank, meaning that it's never going to exponentially decay. It's just going to sinusoidally oscillate forever. Yeah. All right. So just to double check things here, I hope everyone can easily see that REQ in this case is 10 in parallel with 10. Are we good? So that's going to look like 5. So alpha is REQ over, no, that's not right. 1 over twice REQ times C. So that's 1 over 2 times 5 ohms. 1 farad is 1/10 or 0.1 nepers per second. Omega naught is going to be the square root of 1 over LC is the square root of 1 over 1 Henry times 1 farad is 1 radian per second. Omega naught is greater than alpha, so we're good to go there. Omega D is going to be the square root of omega naught squared minus alpha squared. So square root of, nope, wrong button. .995 and some change radians per second. All right, so now let's analyze things at t is equal to 0 minus. Just a poorly drawn equal sign. All right, so at t is equal to 0 minus, our switch is open. So we have this circuit. Our inductor looks like a short. Our capacitor looks like an open. Here's actually V of 0 minus, IC of 0 minus, IL of 0 minus. V of 0 minus is 0 volts because it's the voltage drop across the short circuit that is the inductor. IC of 0 minus is 0 amps because it's the current flowing through an open circuit. IL might have a value, but in this case will obviously be 0 amps because our inductor wasn't connected to anything important. So anybody have a problem with our analysis at 0 minus? All right, now at 0 plus. So at t is equal to 0 plus, our switch is going to close. So our 2 amp source in parallel with our 10 ohm resistor gets connected to our other 10 ohm resistor. Because no current was flowing through our inductor, it's going to be an open circuit. Because there was no voltage drop across our capacitor, it's going to be a short circuit. So here is V at 0 plus, IL at 0 plus, IC at 0 plus. So V at 0 plus has to be V at 0 minus is 0 volts. IL at 0 plus has to be IL at 0 minus is 0 amps. IC at 0 plus can be something different. So what is it in this case? 2 amps. All of the currents will flow through the short circuit that is representing the capacitor in this case. All right. Anybody have any questions, comments, or concerns regarding our analysis at t is equal to 0 plus? So now we look at t is equal to infinity. So at t is equal to infinity, here's our 2 amp source. I'm going to be lazy and just draw a single 5 ohm resistor that doesn't impact anything. Our inductor is going to be a short circuit. Our capacitor is going to be an open circuit. Here's V at infinity, IC at infinity, IL at infinity. We can see very easily that V at infinity is 0 volts. IC at infinity is 0 amps. IL at infinity is 2 amps. Anybody have questions, comments, or concerns? All right. So we already did all of the grunt work, proving that this circuit is critically damped and all that kind of stuff, solved for omega D. So we can jump right into the response part. We're solving for the capacitor current, if memory serves me correctly. So our capacitor voltage is going to be Y of t, and our capacitor current is going to be related to dy by dt. So V of t will be B1 cosine omega dt plus B2 sine omega dt. All of this multiplied by e to the negative alpha t. So V at 0 plus is going to look like, plus V at infinity. Missed that. So this is going to look like B1 plus V at infinity, right? Because cosine of 0 looks like 1, sine of 0 looks like 0, makes this whole second term go away. E to the 0 looks like 1. So the only thing that survives out of this whole big expression is just B1. So V at 0 plus was 0, V at infinity was 0, so it seems like B1 must be 0 volts. Let me double check that. Yep, 0, 0, and 0. Okay. So now we need to do our derivative-based relationship. So IC of t is going to be C times the derivative of V of t, which is going to be C times, let's see, I think it's B1 minus alpha, excuse me, B2 cosine omega dt minus, no, I think I have that wrong. Omega d B2 minus alpha B1. Yep. Thank you. E to the negative alpha t. All right. And so IC at 0 plus is going to be C times omega D B2 minus alpha B1. Because at T is equal to 0, the sine term goes away and the e to the negative alpha t goes to 1. So the only part that survives is this guy right here. Right? So since we know that B1 is 0, I can just cross all that business right there out. And I can say that B2 is IC at 0 plus divided by omega D times C. I believe the algebra there is correct. So IC at 0 plus was 2 amps, if memory serves me correctly. Yep. Omega D was 0.995 radians per second. And then C is 1 farad, where a farad is an amp second per volt. So we can see very easily seconds cancel seconds, amps cancels amps, and we're left with B2 in units of volts, which is exactly what we would expect. So 2 divided by my previous answer is 2.010 volts. From here, IC of T is going to be C times omega D B2 cosine omega dt minus C times alpha B1. Nope, alpha B2, sorry. Sine omega dt e to the negative alpha t, where since B1 was 0, I just threw away those terms so that I know what to put in my calculator to calculate those coefficients. So 1 times 0.995 times 2.010, 1.999995, effectively 2. And then alpha was 0.1. So 1 times 0.1 times 2.01 is just this with the decimal place moved over 1. Yeah. All right, so let's throw this in LT space. Close that. Anybody going to be perturbed if I am lazy and just put a single 5 ohm resistor in here?
reason why the capacitor was blocked.
Because these people hate me and symmetry as a whole. Is the only thing I can think of. It drives me crazy too. In fact, at some point, I will be not lazy enough to make my own symbol that is the right number of units. But today is not that day. Oh yeah. All right, so our resistor is 5, our inductor is 1, our capacitor is 1. I'm going to put ground at the negative polarity terminal of my capacitor, which is the bottom node. I'm going to label the positive polarity terminal of my capacitor as VC up here. My initial condition is the voltage at node VC, started at 0, and the current through my inductor L1 also started at 0. Let's see, alpha is 1/10 of a second. So let's look at this for like 10 seconds-ish. See if this is enough to make things settle. We're looking for our capacitor current. It doesn't look like it's settled yet, so let's change the simulation command to 50. See, that might be too much. It's actually not quite long enough, but it's good enough for us. It's definitely starting to settle to 0. Okay.
For L1.
I'm sorry, restate your question?
I said, so when you write that command down there where it says ICI of L1, still write
We
that?
still, yes, we still very much have to take into account any stored energy in both of our energy storage elements, regardless of what we're looking for. So we should always have an expression for the voltage drop across the capacitor at T is equal to 0 minus, and the current flowing through the inductor at T is equal to 0 minus.
When I was trying to write it on the homework, I was writing IC of I and then write C on there, equal 0, but I just kept getting here.
That's probably, yeah, so I think the only things you should be able to set the initial conditions on are capacitor voltages and inductor currents. All right, so I am going to change the color of this, and then I'm going to, it's not going to be obvious, but I'm going to intentionally make a mistake. So I'm going to add my traces. So let's see, I should have open parentheses 2 times cosine of 0.995 times time minus 0.201 times sine of 0.995 times time, close parentheses, times exp of negative 0.1 times time. Is that the expression that we got? So my coefficient for my cosine term was 2. Omega d was 0.995. The coefficient for my sine term was negative 0.201. Omega d still 0.995. Alpha was negative 0.1. Everything seemed legit there. So I said that I've intentionally made a mistake. It doesn't look like I've made a mistake at all in typing this in. That being said, when I press OK, it is very much not what I expect. So the mistake that I have made is that I forgot that LT spice does everything in terms of degrees, and omega d is an angle in radians per second. So everywhere that I have omega d, I need to add 180 over pi. And now, all of a sudden, everything is fixed. my red curve completely overlaps my blue curve. So typing in the expression as we solved for it gave us a problem, and it's because we weren't considering how LT spice interprets things, right? LT spice, as I mentioned previously, all angles are expressed in degrees, and it does nodal analysis effectively. So we have to keep both of those pieces of information in the back of our mind when putting in our mathematical expressions if we want things to come out correct. All right, so at this point, we have worked an example of a series RLC circuit that was critically damped, a parallel RLC circuit that was overdamped, and a parallel RLC circuit that was underdamped. So we're good, I think. So Friday is just answering you guys' questions. So if you feel comfortable and you're able to work all of the homework assignments, so homework assignment 8, I think, which is due Friday, I'm gonna put homework assignment 9 up today, as well as the submission portal for your in-class testing or your take-home testing. If you're able to work all of those problems with no issue, there is really no point for you to come to class on Friday unless you just really want to hang out.